This is the sixth in a series of videos about simple electronic devices. We will look at semiconductors here, and diodes in particular. Most commercial semiconductor devices use either silicon or germanium lattice doped with a small percentage of atoms from some other element to provide charge carriers. Silicon is from group 4 on the periodic table and forms a network solid. If we try to draw a Lewis dot representation of pure silicon in 2 dimensions, we have something like this. Each silicon atom has 4 valence electrons and shares them with 4 neighboring silicon atoms to form covalent bonds. Since the bonding is very stable, the electrons are not very mobile and therefore do not conduct electrical current well. Note what happens if we introduce some atoms from a group 5 element, such as arsenic. Arsenic has 5 valence electrons, so after bonding to 4 silicon neighbors, the arsenic has an extra valence electron that is fairly mobile. The energy required for this electron to escape its parent atom is fairly small. We call the material in which electrons are mobile enough to serve as charge carriers N-type semiconductors, since the electrons are negative. Alternatively, the silicon lattice can be doped with atoms from group 3, such as boron. Since boron has only 3 valence electrons, substituting a silicon with boron leaves 1 bond electron deficient. We say that a hole has been formed. An electron from a nearby silicon can move fill the hole, but it leaves a positively charged hole behind. Then an electron from a neighboring atom can hop into the new hole, and the process can repeat itself many times. In a sense, the hole is migrating. We call this a p-type semiconductor because holes are thought of as positive sites. Note that both types of material are neutral overall. Interesting things happen when we bring p-type and n-type material together. Some electrons from the n-type material move across the junction into the holes in the p-type material, creating a net negative charge along the interface. At the same time, they leave positively charged atoms or holes behind in the n-type material. Eventually, the charge builds up to repel any further jumping across the border. So near the junction or interface, we have a net excess of negative charges build up in the p-type material and an excess of positive charges build up in the n-type material. This charge separation establishes a potential energy difference across the junction. So we have a net excess of positive charges on one side of the junction and a net excess of negative charges on the other side of the junction. Overall, the device is still neutral. Now let's put metal contacts on the ends of the N and P-type material and see what happens when we try to pump current through the material across the junction with a battery. Before we close the switch, there's no current. The charge buildup across the interface presents a potential energy barrier to the flow of charge. If we close the switch, we find that the negative end of the battery is attached to the p-type material where negative charges already are built up. We are trying to push electrons into an area where an excess already exists. The potential energy barrier grows even larger. This situation is called a reverse bias condition. Consequently, little or no current flows. If we connect the battery in the opposite direction, electrons are pumped into the n-type side of the junction where they can recombine with the holes that have collected there. A similar process occurs on the p side. Electrons are drawn off toward the positive side of the battery. So the potential barrier is pulled down and the current can move easily from one end of the semiconductor to the other. This is known as the forward bias condition. What we've just seen is a diode junction. A diode is a semiconductor one-way street for current. It has a low resistance in one direction. After overcoming a small 0.3 to 0.6 of a volt forward bias voltage requirement and a high resistance in the other direction. Here are some examples of commercial diodes. Looking closely, you can see that a band of black or silver appears around one end. This tells us the forward bias direction. Current moves through the device toward the band, left to right in this picture. In the schematic symbol for a diode, the arrow points in the forward bias direction. When we apply a voltage in the direction of forward bias, there's a small 0.3 to 0.6 volt threshold before the diode turns on. Then the current climbs linearly, much like an ordinary resistor. When the voltage is applied in the opposite direction, only a very small current flows. However, if we apply a very large reverse bias voltage, the diode barrier eventually breaks down, and current flows easily beyond that point. This property is actually exploited in Zener diodes, which break down at well-defined voltages. A Zener diode can be used to regulate the voltage at a given point in the circuit so that the voltage there never exceeds a designed limit. For example, one can buy Zener diodes that have a breakdown limit of 5 volts. In the circuit on the right, the voltage output is regulated so that if the voltage on the left exceeds 5 volts, it's cut off. This protects devices downstream in the next stage from damage.